In Creo Parametric 7.0, PTC has introduced a new application for generating optimized designs focused on different manufacturing methods. This application is called Generative Topology Optimization, and it's powered by Frustum's topology optimization and simulation algorithms, allowing you to explore different design solutions based on critical goals, materials, physics, and manufacturing constraints. Let's take a look at the new application and explore its capabilities. On the screen is a bracket part, which we'll use to walk through the optimization workflow to show how easy it is to set up and generate your designs. Under the Application tab, you'll see a new icon for Generative Design. Selecting it will open up a new ribbon and generative tree, which we'll use during the optimization process. The first step in the optimization is to define the design space for the optimization study. The starting geometry represents the volume for which the geometry will be created within. Selecting the icon and the body, you'll see that it is turning transparent, representing that it's the starting geometry. Next, we'll choose Preserve Geometry. This represents the bodies that will not be affected by the optimization design. Selecting the three bodies, you'll notice that they'll turn blue. Lastly, we'll define the Exclude Geometry. This represents certain bodies that lacked as obstacles during the optimization. Selecting the body, you'll see that it'll turn red, representing excluded geometry. In the model, you'll notice that a load case has already been applied to the two shaft bodies. As they are not designated as preserved or excluded geometry, we'll need to create a contact interface between them and the starting geometry. This will allow the loads to be transferred from the shaft bodies to the starting body to be used in the optimization. Now we'll add a new load case. First, we'll add a constraint to the slot hole by selecting all the edges. Then we'll create a new force load applied to the bottom of the preserved geometry surrounding the shafts. For this load, we'll define it as a 3,500 Newton force in the positive direction. Now that we've defined our design space and our physics, we can create now one or many design criteria methods for the optimization. The design criteria captures the design goals and objectives, geometry constraints, manufacturing constraints, and materials to be considered during the optimization. In our example, we'll set the goal to minimize the strain energy of the design with a target mass of 30%. We'll also apply a design constraint of planar symmetry about the right datum plane. For the material, we'll simply leverage the material that has already been applied to the part. With all that set, we can now run the optimization. As the solver is processing, you'll dynamically see the results appear on the screen as it's progressing through its optimization. Once finished, you can utilize the validation tools to interrogate the results by showing the stress and deformation fringe plots on the model. In addition, you can also show the model's min and max values represented by blue and red circles surrounding the particular areas on the model. Lastly, you can also move your mouse over the model to probe the values at that particular location. Once satisfied with the optimization, you can output the results to a new model through the reconstruction process. Reconstruction will create a fully featured solid model preserving the analytical geometry and optimization results. This will allow you to continue to evolve your design and utilize it downstream. If a change is required, you have full access to editing any features in the part or changing the optimization definition. In our example, we'll modify the sketch used for the excluded geometry. Once you edit the sketch and regenerate the model, you'll notice that the generative design feature is out of date. Editing the design study, we can rerun the optimization or make further changes. In this case, we'll edit the design criteria and add the option for build direction. Selecting the Add Constraint pull-down menu, we could choose Build Direction and choose the top datum plane as the specified build direction plane. Changing the critical angle from 45 to 35 degrees, we could click OK, and now we're ready to rerun the optimization. With the new results shown on the screen, we can perform reconstruction and update the part. Using generative topology optimization will increase engineering's productivity and improve innovation. The result is a design which is optimized for efficiency and manufacturability in a way that a human designer could not easily produce through traditional methods.